let us start this lecture, a thought process from a very great person, Gibran, and who says that no man can reveal to you thought, but what which already lies have asleep in the dawning of your knowledge. This is similar to what the thought process in our Vedas are there. The knowledge lies in your mind already. And if he, the teacher, is wise, he does not bid you to enter the house of his wisdom, but leads to you to the threshold of your own mind. That is a very important statement, and then you should keep in mind that we always thrust upon our things on the others, but rather we should help people to realize their own potential. So, before we will now recall what we learnt in the last lecture. We basically looked at data tables, for example, like superheated steam table and saturated temperature table and saturated pressure table, and also seen how to use those data for and evaluate it, and if it is not available the data, and then we can interpolate using linear interpolation, or you can extrapolate also if it is required. And we have looked at if compressed liquid table for the properties is not available, you can use the saturated temperature data table. And we have looked at also the equation of state, and we discussed in the last lecture like ideal gas law, which you are familiar with, but we looked at range of pressure and temperature under which one can apply it, and under what condition you should not apply, because it will incur error. Now, we will look at that other equation of states, what people have this thing. Now, we need to ask like what you call whether this, what do you mean by real gas, and then because the earlier that equation of state was basically used for ideal gas. So, we know that molecular forces of attraction do exist between among the molecules or between molecules, and molecules have a definite size, right, and we cannot really neglect those things, and particularly at a high pressure and low temperature. And keeping that in view, the Clausius, he proposed a equation of state, in which case he says that like molecules will be occupying certain amount of volume. So, then he proposed, he made a correction like that free volume available for a molecular motion in a container or any other things will be V cap minus V instead of simply V, right. And then B is basically a measure of volume occupied by the gas molecules, and as it is occupied, then the total volume of the container minus that will be the for V which will be available for the molecules to move around. So, then he modified the ideal gas law in this form, and that is basically known as the what you call the Clausius equation of state. This is the Clausius equation of state, right. So, and later on like Van der Waals who proposed another equation of state in 1873, and he modified the pressure term, and considering that he assumed that in a container like in the molecules, if it is at the center like here, it will be acted upon by other molecules, that forces will be in balance these molecules, whereas if it is nearby to the wall, what will happen, and that will give me the pressure which will be bumping into the wall. But however, these molecules will be attracted by by the upper portion any molecule will be there, or this portion, or also sidewise layers, whatever it will be there, adjacent layers. Of course, it is a ideal situation, like where the layer we are talking, but in real situation you can think of it will be attracted, but the other side on the wall there is no attractive, because nothing is there near the wall, no other molecules of the if you consider any fluid, it will not be there, because there is a solid surface. So, as a result he says that pressure, whatever it is, like it will be basically the change in pressure P dash minus P will be inversely proportional to the specific volume, and then he put a constant, and then the pressure what will be acted upon is equal to the, this is the what you call ideal pressure, and this is the correction what he has done. And then when I apply this thing here in the equation of state, I will get a relationship like this, which is nothing but P plus A y divided by nu square into nu minus B is equal to R u t. So, this equation is basically known as the van der Waals equation, and keep in mind that P dash is the pressure of gas in the absence of attractive forces, particularly you can think of ideal gas pressure, if ideal gas law pressure or ideal gas pressure, and P is the actual pressure by the real gas. So, this equation if you look at, it is little complex, and question arises how to evaluate this A and V, which are constants, van der Waals gas constants, and how to go about it. As of course, one can conduct experiments and do that. You can vary the pressure, you can vary the temperature, particular volume. So, if you do that, one can really find out, isn't it? If I take a specific volume, particular volume, I go on changing the pressure, and then temperature will change, right, and then we can evaluate. So, and these van der Waals equations can be applied not only for the gas alone, but also for liquid and the mixture of gas and liquid, this can be applied. But ideal gas law is only valid for the gas. Okay. So, we can rearrange the van der Waals equation in the manner like this. I can write down P is equal to what you call R u t divided by V minus V minus A by V square, right. This is a specific volume what I am saying V, and if I plot this pressure versus what you call the temperature, I can get a straight line, isn't it, because if I assume this volume is remaining constant, I can conduct experiment, and then that what you call this intercept, and also the what you call the slope will be nothing but R u V minus B, right. Sometimes I call this V as nu, okay, nu kappa nu, and the intercept is nothing but minus A by V square. If I obtain this thing, if I know this R u, of course, universal gas constant and this volume we are keeping constant in the experiment, I can calculate very easily, or I can determine the B very easily. And similarly, from this term, right, I can get this A constant, right, values, because this I will get these values, and then I will get this A over here. So, I can get those constant and use the equations, right. And if you look at these van der Waals constants are given here in this table, you can note that the air is something 135.8, right, and whereas if you look at the ammonia is very high in this case 423, and hydrogen interestingly is very low, right. And similarly, in this case it is low, but all these values are of course similar order. If you look at 0.0364 and then this thing. If you look at this B, what it B indicates? B indicates the measure of the volume occupied by the molecules, right. And of course, the carbon dioxide is little heavier molecule, therefore, it is higher, right. And if you look at the hydrogen being a lighter gas, like if you look at it is having a low attractive forces, A indicates that how much attractive forces will be, that will be dictated by that, and is low, and whereas the ammonia is having a higher values. So, let us look at these things, van der Waals equation, and in this case what we will be doing, we are basically look at this equation, and you can see from this equation that basically the volume wise it is a cubic, cubic equations volume wise, right. And then if the temperature is greater than T c, it is really one kind of things, otherwise it will be having this cubic equation here when temperature T is less than T c, it is having 3 values, one is here one can think of, and then another is here, right, if you look at, and another is here. Now, that is the prediction for when T is less than T c, but is it right? Because that this equation, this line is predicted by van der Waals equation, right. But now, if you conduct experiment, it will not replicate the values where it is, this is having, it is going down, and then pressure again going up, and then reach a maximum value again going down. This is basically weight mixtures, liquid and vapor mixtures, where it is not working. And if you look at this is a prediction, but actual experimental data will be somewhere like that. These are my experimental data, like you can say that these are experimental data. Now, it is not. So, therefore, this solution one should not really take this, rather one should go by the experimental data, and experiment data says that pressure is remaining constant at the pressure, at this pressure the temperature, saturated temperature will be remaining constant, because vaporization process is taking place, right. So, therefore, one has to careful about using this kind of thing, and then from the stability point of view, we are not discussing that, one can say that this portion of the curve is not really possible in reality, right. So, therefore, we will discard this portion, however, in this region and this region it is working fine, and this is van der Waals equation will be working in this region well, and till up to T is equal to T c, that is isotherm like it will be working. And you will also find that in this region it will not really work much, as you go along we will see. But wherein the superheated regime, like this is your superheated region, right. Vapor region, right. So, in this it will be what you call doing well. So, every equation of state must satisfy the following condition. What are those? That is, the when pressure tending towards 0, it must reduce to a ideal gas law, right. When pressure is very, very small, right, then ideal gas law should be valid. Whatever equation of state you see, for example, we have seen the van der Waals equation of state. That is the one condition, and beside this the critical isotherm must have an inflection point. So, what is that inflection point? If you look at that, this is my inflection point, slope is changing here. Are you getting? The slope is changing here. This is my inflection point. The critical point should have an inflection. So, that should be satisfied, and critical point, the highest pressure and temperature at which a liquid and vapor phase coexist in equilibrium, that we have seen. That means, in that critical point, that what will be the condition, what has to be valid or what has to be satisfied is dou p by dou V c when temperature is constant, that is the critical temperature is equal to 0. Not only the first gradient, rather the second gradient also will be equal to 0, and this condition has to be satisfied at the critical point. So, question arises, we have seen that how you can evaluate the conduct experiments, and then, but let us look at how we can evaluate analytically. So, with the van der Waals equation, we can rewrite that in terms of pressure, just this thing, that pressure is equal to R u T divided by V minus V minus A by V square, and then I can take a derivative of this expression with respect to the specific volume while keeping the temperature. I can get, that is dou p by dou V at T c is equal to minus R u T c divided by V c minus V whole square plus 2 A divided by V q at, of course, the critical point we are evaluating. So, therefore, I am putting the specific volume at critical point, and then we can also take the second derivative of this things of the pressure, and we will I am sorry. So, from this expression, like we can get 2 A by V cube c is equal to R u T c divided by V c minus V whole square. And what we will do now, we will take the second derivative of the pressure, and from this expression, and we will get is the second derivative of the pressure with respect to the specific volume at constant temperature or the critical temperature is equal to 2 R u T c divided by V c minus V whole cube minus 6 A by nu 4 at critical condition is equal to 0. From this expression, we can get a relation between the 6 A by nu 4 is equal to the 2 R u T c divided by specific volume at critical condition minus V whole cube. So, from this, using this what you call equation 1 and 2, we can get the V c is nothing but 3 V, right. That is a very important relationship, that specific volume is equal to 3 B. We are evaluating at the critical condition, and by substituting these values in equation 1, we can get A by B is equal to 27 by 8 R u T c. And but we know that like that P c, the pressure at the critical condition will be nothing but R u T c divided by V c minus V minus A by V c square. And what we will do? We will basically we will use this expression V c is equal to 3 B, like we can find out that this is nothing but your 3 B, and that became 2 B, and what do you, I mean that became 2 B, and then in place of this V C, I can also use this is nothing but your 9 B square, and then that will get expression. And if you look at, we have already seen P C is equal to this, we have already seen that, and A B by 27 by 8 R U T C, and then we will use this expression, and R U T C by 2 B in place of this expression, we can use this A B. In this we can use A B here, and from this expression we can use, and I will get basically 27 R U T C by 72 B, and then when you simplify you will get R U T C divided by 8 B. And from this expression, from this I can get B is equal to R U T C divided by 8 P C. And knowing this thing, and also using this expression A by B, I can get this relationship, which is nothing but A 27 R U square T C square divided by 64 P C. And if you look at, if I know this what you call critical temperature and critical pressure, I can evaluate A for a particular substance, right. And of course, if I know this A, I can find out also the B, right, a similar manner. And if you look at, if I and at the critical point, if I know this volume, specific volume, and P C R T C, if I put these values, I will get this, we call it as a compressibility factor, right, which will indicate how much it is deviate from the ideal gas law, that is nothing but 3 by 8 0.375, right. This is the condition what we will be getting, and the Z is considerably higher than the actual value of any substance, but this will be true for that. And as it will be, this will be deviating from the what you call the values, and we will be discussing more about this compressibility factor whenever we are discussing how to use the ideal gas law and make a correction for this compressibility factor, so that you can use ideal gas law very easily for real gas. Besides this, there are several number of what you call ideal number of equation of state being devised for treating the or for dealing with the real gases. So, one of them is Beattie and Bridgeman equation of state, which was being proposed by these two persons in 1928, and that is basically if you look at, that is P is equal to R U T divided by V square into 1 minus C V into T cube multiplied by V plus B minus A by V square. So, if you look at in the Van der Waals equation, there are two constants. In this case, how many constants? There are total 3 constants, A, B and C, capital A, B and C, right, and small c. So, whereas A is equal to A naught 1 minus A by nu, and B is equal to B naught 1 minus B by V. So, if you look at now this constant, actually the constants are inside constants. So, therefore, total whatever you could see is total 5 constants, like if you look at B naught, A naught, A, B and C. So, there are total basically 5 constants for this as compared to the Van der Waals equation. So, these constants can be obtained like for various substance, people have found out and given in a tabular form, and you can use, and this equation can be used reasonably till the density is up to the 0.8 of the critical density. That means, when around critical point you cannot apply this equation, right. It will be away from the critical point where you can apply this equation and with reasonable accuracy. So, these are the data table one can think of. There are total what you call 5 constants are being given here, and for various substances, and these substances will be varying like different values. For example, air is A naught is 0.1318, and whereas you can get butane which is 1.8, very high values, right. And of course, helium is having a very small value. So, it varies a lot, and similarly B naught also, like butane is having highest value here, and air of course 46.11. So, one has to be careful about this, not only the values and also the what you call their units is very important. So, that one has to be careful about using this equation of state. And let us look at Benedict-Webb-Rubin equation of state, which was given in 1940, and this is having a very what you call little more complex equations and having this. So, if you look at the first term, if you look at in each equation will be similar, RUT by nu, plus there is another lot of other terms are there, and having this is the first term, and this is the second term, and the third term, fourth term, fifth terms, like kind of things, and having lot of constants. So, these 8 constants are given in this, and this equation can handle substance at densities up to 2.5 of the critical density, right. That means, this is a little better than the earlier equation of state. And of course, the 1962 Strobes improved this equation by using 16 constants, like, and there might be several others which are having more number of constants, and there is the table which you can see in the textbook and other books also, you can use those tables. I am not expecting that you should remember this equation, it is not that easy to remember, but however, you should know how to use and where to use, that is important. And there is another equation which is the Redlich-Kwong equation of state, and it is more accurate and simple equation of state, and it is used very what you call profusely by the chemical engineering people to handle the mixtures, which is simple, very simple. Like if you look at it, is similar to that of the van der Waals equation. It is the P is RUT divided by nu minus B and minus A divided by V into again multiplied by V plus B and T power to 0.5. So, if you look at it is similar, but not same, and AB are evaluated from the critical temperature and pressure, and this is the relationship what is given here, and keep in mind that you need not to remember this thing also. A is equal to 0.427 R square, that is universal gas constant, and T c power 2.5 divided by P c, and similarly B is relations are given. So, if you can note that A B is basically dependent on the P c and T c, and you can get the table for the critical temperature and pressure, and you can evaluate very easily. So, therefore, there is no need to have table. If you know the data for the critical pressure and temperature for a particular substance, you can evaluate very easily these constants. So, beside this, if you look at, there is a people are always very much what you call interested to have a simpler form of the equation of state similar to the ideal gas law. So, they thought that why not you extend that ideal gas law, and people have done that, extended the ideal gas law and putting lot of what you call series form, expressing it in a series form, and that is the equation what we call P V by R U T is equal to 1, And then there are several kind of thing, if you look at it, similar to your other series which you might have used, like your binomial series or the Taylor series, not that way, but at least series wise I am saying. So, B t divided by nu plus C t what you call velocity square and d t velocity cube, and these are all what you call constant, which is a function of temperature. You need to evaluate that or in a tabular form. So, if you look at, if I will neglect these terms, these terms, this is this or in other words the first term, this term is nothing but what? Your ideal gas law, right. So, this is your ideal, rest of the things you are doing some addition, so that it will be more correct one, or the accuracy will improve as you go for the higher pressure and low temperature gases kind of thing. And where the B and C and D are known as the second Virial constants, and the third and fourth and respectively like that. And we see basically this Virial constant describe how it is different from ideality, because ideal is this one, right. And then as you go on, and then you add the accuracy to that, and PVT data can be improved by including more number of these Virial constants. But experimental values for the second Virial constant for number of gases are available, but the third and fourth one are not available. So, you people are working on that, they may having, and the Virial and the ideal gas laws to state have a strong theoretical base. For example, like whatever the equation I have shown for the real gas, except the van der Waals, like your Benedict equations, and then Redlich-Kwong Equation and Rubin equations and other things, they are having no what you call theoretical basis, they are semi empirical relationship what people have developed, but whereas it is having. So, therefore, people do use it and to improve, because. So, I will just make a comparison how good it is, if you look at that this thing, if you look at the Virial equation will be here, when this plotted P by P c by V by V c at a temperature 270, and these are experimental data, right. The van der Waals equation lying very closer, if you look at a higher this volume ratios, it is almost close, but ideal gas law is far away. That means, if I consider this one, error will be too much, error will be this much error, this will be an error, when you use the ideal gas law instead of actual, and because experiment shows this, and experiment is very close to the Virial equation, therefore, one can think of using that. But if you are in this regime, okay, I am like one can use, but little bit error will be there. So, therefore, one has to be careful when you are using the what you call the gas laws. So, as I told that van der Waals equations having two constant and accurate over a limited range, and Beattie and Bridgeman 5 constant, which is accurate for when the density is less than the 0.8 critical density, and Benedict and Webb and Rubin equation 8 constant accurate when the rho is less than equal to 0.5 critical density, and Strobe's equation 16 constant, more suitable for computer calculation, because hand calculation is difficult to have. And of course, the Virial equation may vary depending upon how many terms you are taking extra than that of the first terms or the coefficients you are considering. And if you look at that, that means percentage of error involved in various ways. One can evaluate table, you can use equation of steady state table. You can look at from here, these are the of course, the saturated vapor line, and you can see that van der Waals equation, first one is a very low, like very less percentage, and all are giving the good result in this regime. But as you are coming closer to this saturated line, you see that van der Waals is giving something 0.4%, and whereas these are 0.1. But if you go to the, this is the low pressure, what is happening, but if you go towards the higher pressure and this is the critical point here, you find that error is very, very high. In the van der Waals equation give you 11.6% and 6.3%, and this is 1.2%, like that is the Benedict-Webb-Rubin bottom one. So, similarly, there are I am sorry actually. So, this other way around, this point is basically 7.3% give the van der Waals equation, because all are evaluated at the what you call critical point, whereas the Beattie and Bridgeman will give you 59.3, and Benedict and Rubin this a very little bit improvement will be there, right. If you look at these are the things which will be talking about, but however, here nearby it gives that van der Waals equation gives more percentage kind of things. Like for example, if you consider this point, it gives the 11.6 the van der Waals, and Beattie and Bridgeman is 6.3 and 1.2, it gives the Benedict and Rubin kind of things away from the critical point. So, if you look at, one has to see where to apply and which condition, and then one can use the equation of state. Otherwise, if you are not what you call having the regime where you can apply the equation of state, either the van der Waals or any other equation of state, you need not to use, rather go for the steam table or the any other table, for example, refrigerant tables or refrigeration table kind of things. So, now let us take an example just to illustrate this point, that which one has to choose. So, for example, 1 kilomole of ammonia is contained in 0.6 meter cube at temperature of 200 degrees Celsius. We need to estimate pressure developed by the gas using the ideal gas law and van der Waals equation and Redlich and Kwong equation of state. So, if you look at the number of moles is given 1 kilomole and volume is given, temperature is given, we know the universal gas constant, right. So, and we can find out pressure very easily, right. P is equal to R u T, V kappa is nothing but volume per unit mole. So, if you substitute these values, you are getting 6.55 or 6.56 megapascal around. And if I will van der Waals equation will use for ammonia, from the table I will get this A is 423.3 kilopascals and B is 0.373 meter cube per kilomole. And what I will do, I will substitute these values in the van der Waals equation, and what you call this is basically R u universal gas constant, and temperature I know this universal gas constant, and this temperature is given, and this is the volume is given, and this is the correction for the volume is given, that is nothing but your B, and this A is known, and then this volume is known, you will get 5.815 megapascal. If you look at it, is different than the ideal gas law. So, let us look at Redlich and Kwong equation of state, and we can evaluate A values here, and we know this T c we can find out corresponding to the ammonia, and so also the P c, and we can this happens to be 405.6 Kelvin and P c this thing, and when you substitute these values, right, you will get the A and B from there, and if you find out this 5.7885 megapascals. If you look at 3 different pressures you are getting from using this. Now, one has to also worry about that which one has to be used, right. So, of course, in this problem we are not worried about what is, but I am saying that this pressure evaluated by different equation state is basically is different. So, what we have done till now, like ideal gas law is being used profusely, and ideal gas law is being used profusely because it is quite simple and elegant to use, but it holds good only for the low density gases or basically the low pressure or the high temperature gases, right. So, now as we have defined a compressibility factor, which is basically the ratio of actual volume divided volume occupied by the ideal gas. If we assume the gas to be ideal, the volume will be occupied, that we call it as a volume of ideal gas. So, if I use these factors, V actual per, of course, this volume is the per unit mole, then this is the ideal. I can use this ideal gas law and I will find out Z is nothing but P into V kappa divided by R u T. And this factor, if it is equal to 1, what will happen? If Z is equal to 1, that means it will be same as that of the ideal gas law, and if for a particular this thing, then ideal gas law will be valid. And basically, if you look at Z is a function of what? Pressure and temperature, right. And what we will do? We will have to look at that compressibility factor if we will plot versus pressure and for different temperature. Let us say nitrogen I have considered, right. And if you look at, if I take this 300 Kelvin, this line is here, and after that it goes on increasing, right. And if I take, this is your saturated vapor line, right, and this is a critical point, this saturated liquid line, at different temperature it will be like that, this goes on. Now, from this plot one can say when I can use, particularly if you consider nitrogen, and nitrogen percentage in the air is quite high. You can consider the air will be behaving similar manner that of this compressible chart for nitrogen, right. From this plot, looking at if my temperature is ambient, right, then at what pressure I can use the ideal gas law? Can anybody tell me? Look at this chart and tell me. See, what you will have to do? You will have to see that where the Z is equal to or closer to 1. For example, if I take 300 Kelvin, right, 300 Kelvin, that means I can think of using here very happily, something around 10 kind of megapascals I can use very happily ideal gas and 300 Kelvin. If I increase the temperature, let us say to 1000 Kelvin in the combustors, in the other places it may occur, right. What will happen? I can happily use the ideal gas law. Are you getting my point? Means 100 atmospheric pressure roughly, it is good enough. If I will have I can go little further also, maybe till this, if it is I am not bothered about that much of error, let us say something around 5%, then I can. That means safely one can use 100 atmospheric pressure for air at ambient condition. If it is of course the lower one, then one has to worry. If I talk about lower temperature, then one cannot use it, because it can go for a low pressure. For example, 200 Kelvin, it is a error. If I use here, Z will be here somewhere, right. So, Z is away from the 1, and of course, if I going towards the lower pressure, it is reaching this Z is equal to 1, because this is Z is equal to 1. Okay. So, therefore, at a lower temperature I will have to go to the lower pressure, and the ambient temperature for air or the nitrogen, then I can go for the higher pressure around roughly 100 atmospheric pressure. Now, this chart will be different for the different kind of materials, different kind of matter, nitrogen, what you call oxygen, helium, hydrogen. Now, how to go about it? If you will have to use several charts, then it is a problem. So, right, the real gas will be what you call become ideal gas only when Z is closer to 1, and as I told, for real gas Z is not will be different than 1. When Z is less than 1, that actual density is greater than the ideal, because the specific volume of actual is less than the ideal specific volume, and when the attractive forces pulls the molecule together, right. So, that you can have this situation, and when Z is greater than 1, then actual density is less than ideal, because the specific volume of actual is greater than the specific volume of ideal. In this case, molecules are moving apart, that means molecules are going away from each other. So, the Z reveals basically extent of deviation from ideal gas law, right, that indicates how far it is from the ideal gas law. And as I told, that all gases, when considered at a as I told earlier, that each gases will be having their own compressibility chart, then it will be difficult. What people have found out, that all gases, when considered at the same value of the reduced pressure or temperature, will have the same compressibility factor. What is that reduced pressure? Reduced pressure is basically what they say, that one can think of using the critical condition, that is pressure divided by critical pressure will give me the reduced pressure, and the temperature divided by critical pressure will give me reduced temperature, and similarly the reduced volume. And right, then when they found that all gases are now if you are what you call taking with reference to the critical conditions, the properties, the pressure, temperature and volume, using the reduced pressure, reduced temperature and reduced volume, then all these things are coming into one plot. So, therefore, it is this is very important, and of course, the what you call this specific volume is basically actual volume divided RT criticals and pressure. This is known as pseudo reduced specific volume, and Z can be determined from the knowledge of PR and VR. And if you look at, when I plot this thing Z versus the reduced pressure for different reduced temperature, if you look at, there are various gases like methane, ethylene, ethane, propane, butane, isopentane, heptane, several, and water also, that all are coming in the same place. So, this is a very different thing, very interesting. This is known as basically what you call generalized compressibility chart, right, which it can encompass all most of the gases kind of things. So, and of course, the if you look at the non ideal behavior, it will be little bit careful one has to be, because here the gases will not be valid, Z will be different, whereas here it will be ideal gas behavior kind of thing. Gases, as I told, critical point neighborhood is one has to be very careful while handling that we have seen earlier also. So, generalized compressibility chart, if you look at Z is equal to basically function of the PR and TR, and if you look at Z at PR is equal to 1 and TR is equal to 1, ZC is around to be 0.27 for all substances, right. But unfortunately, because we are all defining that way with respect to their corresponding critical temperature and pressure, but Z values will be varying from 0.23 to 0.33. So, therefore, there is a deviation in that. That means, if you use that, you will be making some error as well, right. So, hence it is not very accurate, but however, if it is being used because of its simplicity. And if you look at the compressibility chart, we will be looking like that here. This is for the low pressure of 10 kind of thing, reduced pressure is 10 times that of the critical pressure, actual pressure is 10 times that of the critical pressure. At different TR values is being plotted, like these are corresponding to TR values. So, this is TR, right. So, these are basically TR values which is being used, right. And of course, at the when Z is greater than 1, this is being shown, right. And this dashed line is basically the specific volume. If you look at this dashed line, VR 0.5, 0.253 and other things goes on, these are pseudo what you call critical or the reduced volume, pseudo reduced volume. So, similarly, you can get that the higher pressure range, and in the tutorial class we will be using this compressible chart to evaluate the data and find it out. So, this is the generalized, when you combine both low pressure and high pressure, you will be looking like that. If you look at with the 10 I have magnified, that portion I have seen, this is the low pressure and the high pressure region, right. You can look like this is a generalized compressible chart for all gases, right. What we will do, we will take one example, then we will this thing 1 kilomole of methane is filled with 0.6 meter cube vessel at 200 degree Celsius, and we need to determine pressure in the vessel using the generalized compressibility chart, right. So, if you look at the temperature is given, so we can find out very easily the reduced temperature, right. What is that? T, but divided by the critical temperature. And also a pressure is given, but in the example the pressure has to be determined. So, we cannot find out critical pressure, okay. Am I right? So, we cannot find the we can find out critical pressure from the data of ammonia, but we cannot find out the reduced pressure. But however, if I do not know the reduced what you call pressure, or I do not know the pressure, then I cannot find out the reduced volume. See, this is the problem, but let us find out TR. TR is basically T by Tc, we can get 1.17 very easily. And as I told, since P is not known, PR cannot be determined, but we can express P in terms of PR, right. P is equal to PR into Pc. So, we can get a relationship. If you look at, if I plot P versus PR, it will be nothing but a straight line, right. So, now if you look at, I can get another relationship between Z and putting these values, and it will be what you call Z is, if I put all these values, because specific volume is given, RU given, Tc is given, then I will get Z is equal to 1.72 PR. Again, this is the straight line, Z is a function of PR, which is nothing but a straight line. So, what we will do? We will be getting TR corresponding to 1.17, right. We have already evaluated TR, this is basically capital R, TR 1.17. Then I know that relationship Z is equal to 1.72 PR, I will draw a line here, and wherever it will cross, I will get these Z values, and of course, I can get these PR values here directly, right. And if I know these Z values from here, I can calculate what will be P. Are you getting? That means, getting this what you call the chart itself can be utilized to find out the pressure by doing this relation. So, this is not a very straightforward, little bit twisted. So, I thought that I will show you how you can use chart to do the data for using the generalized compressibility chart, right. And once I know the Z, I can find out very easily the pressure. So, we have seen basically in this lecture how we can handle using various equation of state and how handy it is the compressibility chart, although it may lead to some little bit error, but however we can use it. So, in the next lecture we will be discussing, we will be starting a new topic and then we will stop over here. Thank you very much.